We're going to wrap up here, last little bit here of 11, 12, 14, 16, 18, 19. We were getting into organic chemistry last time. Organic chemistry really is the study of carbon-based compounds. Most organic compounds have basically carbon attached to carbon. And usually attached to those carbons are hydrogens. And as we talked about last time, you know, if you sort of swap out some of these hydrogens for other type of elements, very commonly oxygen, nitrogen, sulfur, and those type of things, we do get different sort of classes of organic compounds, and they are based off of what are referred to as the functional groups. So we ran through, I think, a bunch of different functional groups. We talked about alkanes, which are really the simplest of everybody, which is the carbon-carbon sort of single bond is the functional group. We also have alkenes, which have at least one carbon-carbon double bond. We have alkynes, which has a carbon-carbon triple bond. There's other ones involved, like I said, like oxygens or things that are known as aldehydes, which have a carbon-oxygen double bond and a hydrogen. Also, things like ketones, which have 3 carbons in a row and a double bonded oxygen in the middle. We also have things like amines, which are actually nitrogen-containing sort of groups. Thiols, which are sulfur-containing groups. We got carboxylic acids, which also are these guys. And obviously a few others there that I didn't write down, like our ethers. We also have esters, which look like this. And I think I almost got them all there. I might as well throw them up here. There we go. Do this guy, which is in the mid. So, you know, depending on, you know, what sort of functional group any of these organic guys have, it does really change a lot of the properties sometimes with these organic molecules. Your basic sort of organic molecules, which are sometimes referred to as hydrocarbons, which have carbons and hydrogens only, they're pretty much nonpolar substances. That's because carbon-carbon is a nonpolar bond. Carbon-hydrogen is also nonpolar. So they really are going to be working with the dispersion forces that we talked about, which are those really weak intermolecular forces. But if you put something on it, like I missed actually the alcohol here, if you put an OH group or something like that, which is an alcohol, that is now a sort of a polar group that goes onto the organic molecule. And it does sort of change some of the functionality that that molecule could have. If you have something that has an OH group on it, it can participate, for example, in hydrogen bonding, which is a relatively strong sort of intermolecular force. Also makes it pretty soluble in things like water because it can hydrogen bond with water. But there is sort of a limit, again, if you sort of build out usually above 5 or more carbons in a compound and you got just like one OH group, the solubility, for example, with something like water really does start to decrease a lot because all those carbons sort of get in the way. Also affects things like boiling points and melting points. So again, something like an alcohol would have a higher boiling point and melting point because it could hydrogen bond with itself versus an alkane, which cannot hydrogen bond at all. So it has a much lower sort of melting point and boiling point as well. We got into, I think, the sort of first 10 alkanes, which is really important in organic chemistry because really everything sort of falls back to these guys. And alkanes have sort of a CnH2n plus 2 type of general formula where N is the number of carbons, and obviously you can use it to figure out how many hydrogens. 1 carbon would get you 4 hydrogens, which is known as methane. 2 carbons would get you 6 hydrogens, and that is ethane. 3 carbons gets you 8 hydrogens, that is propane. 4 carbons gets you 10 hydrogens, and that is butane. 5 carbons, 12 hydrogens is pentane. 6 carbons, and then 14 hydrogens there will get you hexane. 7 carbons, 16 hydrogens will get you heptane. 8 carbons gets you 18 hydrogens is octane. And 9 carbons gets you 20 hydrogens, and that is nonane. And 10 carbons gets you 22 hydrogens, which is decane. These are all alkanes, A-N-E. They all end in A-N-E. And as I mentioned, as we saw a little bit the other day, really everything does sort of fall back to these guys. We really just trying to change this name a little bit, depending on the functional group that is present. So it's really important, these 10 names, and it's oftentimes the basis of like everything else we see in different organic sort of compounds. We also talked about a couple of different types of formulas. Obviously, this is the molecular formula here. You could also have a formula that looks something like this. This is what is known as the condensed formula. You could do one where you just basically draw lines like this, and that is what is sometimes referred to as line structure or line formula. And the other one is one where you sort of draw out all the hydrogens, that is sometimes referred to as the expanded structural formula. And I'll just draw methane since it's not a lot of room here. Something like this where you kind of draw out everything is sometimes referred to as the expanded structural formula, kind of like a Lewis structure in a sense. So those are 3 sort of very common sort of formulas we see a lot in organic chemistry. Alkanes can come as what is referred to as straight chains, which means just run straight across there, nothing coming off of them. They could have branch chains, which means there's kind of a main part of it, and then off of the main part are other things that are like branches on the tree. And they also could make cyclic type structures where they basically form rings and kind of close in on each other. A couple of things we also talked about is every time you kind of make a bond to carbon, you do lose a couple of hydrogens. So if you go from a single bond to a double bond, each carbon in that double bond needs to lose a hydrogen to make room. And if you go from double bond to a triple bond, we lose another 2 hydrogens, 1 on each carbon to do so. Super important to remember also that carbon only should have 4 bonds, and that is it. Should never have more than 4 bonds. And it's historically very common. People, when they draw organic things, like to just keep throwing bonds onto carbon, like lots and lots of lines just attached to it. Also, a good thing to remember as well is our friend hydrogen, again, should just look like that. Really 1 line, and that's it. No dots, nothing else. No double bonding, triple bonding, hydrogen, because it is definitely wrong. Any questions on any of that stuff there we talked about last time? So again, here's methane. Some of the other things I think we also kind of touched upon is the geometry that we see. This is again a central atom that has 4 electron pairs. It also has 4 bonds, and that is our tetrahedral arrangement, like we talked about with Lewis structures. And that is a 109.5 degree sort of angle that occurs here. And in alkanes, that's really why we see line structures kind of drawn in what is referred to as sort of a zigzag sort of shape, because they're each tetrahedral. So tetrahedral to tetrahedral ends up giving this sort of mountain or zigzag sort of shape that occurs with alkanes when we draw something like line structure. Ethane has 2, and you can start to see that sort of tetrahedral, the tetrahedral arrangement. You can see if we had another one, we're going to kind of come back up this way as well. And again, given that sort of zigzag arrangement. This again would be our expanded structural formula. This would be more of a condensed formula. And I guess if you wanted to draw a line, it would look like that basically. Here's our propane. And again, you can see as we did add that next one on, we kind of zigzag back up as they are all tetrahedral in that arrangement. Every single carbon atom there has 4 electron pairs and 4 bonds. And again, given that tetrahedral arrangement. By the way, in organic chemistry, typically if you see a wedge drawn, yes. Are the, say again, are they? This guy would definitely be nonpolar because it's all carbons and carbons and hydrogens. Yeah, they're nonpolar. Yeah. All the other ones we saw as well are also nonpolar. That's why, you know, these things, especially the first several organic alkanes, they're gases like propane, methane, butane, and that's because they're all pretty much nonpolar. They're going to be using that dispersion force, which is a really weak force. And that means that they could go into the gas phase really easily. In this case, they actually are in the gas phase under normal conditions because of that. Again, organic, if you kind of see these wedges, that means it's sort of coming out of the paper. And if you see sort of the dash sort of guy, that's like going behind the paper, if you will. So that's sort of what those are, to sort of show the 3-dimensional sort of shape that's happening. Now, both of these here that are drawn are actually propane. And it also is a very common thing that people do when they start drawing some organic things is they're asked, hey, can you draw something different that has like 3 carbons and stuff like that? So they draw it like we see up here, perhaps. We got one on the left there, one on the right. And they go, cool, they look different. So clearly I drew something that is different. And one of the main things that we do when we are going to sort of name something, and that's really a good way to determine whether or not you actually did draw something different, is to name them both. And if you get 2 different names, then you absolutely did draw something different. And if you get 2 of the same name, you just drew something that looks different, but is actually the same thing. Obviously, the key to that would be to properly name both of the things correctly. But when we do go to name things, it's always about finding what is referred to as the longest continuous carbon chain. So when you have a sort of molecule drawn in front of you and you need to go name it, which we're going to talk about all the steps here in just a second, but you always want to find the longest continuous carbon chain. Now, that does not mean that it is the straightest chain. It could kind of go straight, then go up, and then go over. You could have several options to sort of choose from, and you want to kind of choose all the options. And in some cases, you may go one way and get a number, and then go the other way and get the same number. So sometimes you will yield, you know, the same number in multiple directions. The only thing you cannot do is go backwards. So you got to go one way, and then you hit a dead end, and you got to stop, and that's your total number of carbons. You can't backtrack or anything like that. So if we took sort of that approach with these 2 drawings here, the first one's pretty easy to see. We just go straight across 1, 2, and 3 carbons. And that longest continuous carbon chain is going to give us really the base of our name, the base of the name, which in this particular case is propane. And that actually is the name of this guy because there's really nothing else there other than hydrogen. So there's all carbons of hydrogen. So that would be propane. Now, if we look at the guy to the right, again, we may think, well, it is definitely something different because it kind of looks different. But if we take the longest carbon chain approach here, that is 1 carbon to 2 carbons, then we could just simply go down, and that also is 3 carbons as well. So that is a 3 carbon chain. And again, there is nothing else attached there. And that means that this guy here is also propane. So they're both propane in this particular case, even though they may appear different. And it's a very common thing that people will do when they're asked to draw, as we'll talk about here in just a second, what are referred to as isomers. And isomers are guys that have basically the exact same chemical formula or molecular formula, but they have some different connectivity. So some people are like, hey, draw me 2 isomers of somebody with 5 carbons. And they just go, okay, I'll just draw it straight. And then I'll just kind of drop the end of one, and I drew something different. So let's take a look at these 2 guys, which actually are what are referred to as isomers of each other. And if we look at the top guy there, we have, I'll redraw it here. All right, here we'll do that, we'll do that, we'll do that. And there is a hydrogen there at the end. They apparently, when they rehooked this thing up, shifted everything badly. So if we were going to name this, we would take the same approach. We're going to go for our longest continuous carbon chain, which would be 1, 2, 3, and 4. That is going to be the base of our name, which 4 carbons is butane, which is this guy right here. Now, there's absolutely, again, nothing else attached here but hydrogen. So this would be the actual name that we would call it. Now, if we take the guy on the bottom, and let me just redraw it up here. Now, when we go to find the longest carbon chain here, we could go straight across, and we got 1, 2, and only 3 in this case. We could also, if we wanted to, go straight and then go up, which would give us 3 as well. So this is what I was saying before. There are sometimes, multiple ways you could go, and you'll end up with, the same number that's the longest. And does it matter which one you choose? The answer is no, it doesn't really matter which one you choose. Sometimes it's easier just to take the straight one so you can kind of see everything in front of you, but you don't have to. It should give you the same name regardless of which one you choose. So for this one, I'm just going to take the straight one there. So we'll re-highlight that there. So straight across here is going to be our main chain. And then off of this main chain here, we have actually something that is not part of it. It's sort of a branch that comes off of it right there. And that is that guy that is right there. So if we were going to name this, we would start with the longest continuous carbon chain, which is 3 carbons. And that means the base of this name is actually going to be propane because it has 3 carbons. Now, organic chemistry and naming, it's all about telling people exactly where you can find everything. Is pretty much what the names basically are about. So when we look at this guy up here, this is not part of the main chain, the longest continuous carbon chain. This is what is sometimes referred to as a group, and more specifically is referred to as a alkyl group. That's a fancy way of saying carbon-based group, basically. So an alkyl group here is basically a carbon-based group that's not part of the main chain. It comes off kind of like a branch attached to the main chain. And because it's a alkyl group, it is really also based off of those first 10 alkanes. So if we look at that guy that's in green, it has really 1 carbon. And 1 carbon is based off of our friend methane. The problem, though, is if I wanted to use methane as my 1 carbon group and I went to go attach it, say here, would that be a problem for that carbon? It would be, because then that carbon would then have 5 bonds, which is way too many for carbon. So because it's a group and it needs to attach to the main chain, it actually will end up having 1 less hydrogen. And that 1 less hydrogen gives it a place where it can attach, for example, right here, into that main chain and still maintain only 4 bonds. So alkyl groups that are there are really those alkanes that we saw there, methane, ethane, propane. They are those guys missing one hydrogen so that it can bond into the main chain. And we also changed the name from methane to YL at the end. So it becomes what is known as a methyl group. So that is a methyl group, which is based off of methane, has one less hydrogen, allowing it to bond in. So we would actually add that to our name. This is methyl propane. The last thing that we typically do is with alkanes is we always want to give the number where those groups are located on the main chain, which carbon are they attached to. So that usually means you have two options when you go to do this. Do you number the main chain left to right, for example? That's carbon 1, carbon 2, carbon 3. Or you could obviously go the other way, which would be this is carbon 1, this is carbon 2, and this is carbon 3. In this particular example, does it matter which way I go for that guy? It really doesn't matter. They're both at carbon number 2, and that is where the 2 comes from. And the proper name, we'll get rid of isobutane. This name right here, that is 2-methyl propane. The 2 means that if you go to carbon number 2 on the propane chain, you will see a methyl group hanging out there. And that is the name that we have there. So the guy on the left, which is butane, the guy on the right is 2-methyl propane. These are actually different structures of each other. And these are what are known as isomers of each other. They have the same formula. Right above it, I guess. Isomers, try that again. There we go on the screen. Isomers, again, have the same molecular formula, but different connectivity. If you count all the carbons, everybody here has C4 and H10. So everybody has 10 hydrogens and 4 carbons. These are isomers of each other. A couple other things that we typically do when we name, as we'll talk about again here in just a second, but we typically do a dash between a number and a letter. So that's why it's 2-methyl. So we put a dash between a number and a letter. And if you happen to have 2 numbers that come in a row, which can happen, we put a comma between the 2 numbers. We also, for example, in the case of alkanes, always want to number the chain in whichever way gives the groups the smaller number. So we always want the groups to have the smaller number, and that is the way that we numbered the chain. Other things is if there's multiple groups there, we put them in alphabetical order, regardless of any type of prefix or number that is present. If we have multiples of the same group, we use prefixes. So if we had, say, 2-methyl groups, we would call it dimethyl. And again, we would give the numbers for each of those things. Any questions on that there? So as I mentioned, isomers of each other have the same molecular formula, but different sort of connectivity. These are 2 examples as well of 2 isomers. This is an alcohol because it has the OH group there. And this is an ether, which has our carbon, oxygen, carbon. That's an ether. And again, if we counted up everybody here, there are 2 carbons, there are 2, 4, 6 hydrogens, and an oxygen in each of those guys. They have different connectivity. For example, they also would have different properties. Our alcohol there, which is ethanol, has that OH group that we talked about, which again will allow it to, for example, hydrogen bond with something like water through that group, do a little bit of hydrogen bonding, makes ethanol soluble in water. The dimethyl ether there cannot hydrogen bond there because it doesn't have the ability to hydrogen bond with itself. So, you know, it has some different properties depending on sort of the connectivity that occurs. Any questions on that there? By the way, again, you can hopefully kind of see a pattern here. This guy has 2 carbons, which is based off of ethane. It is a alcohol, which ends in OL, and it is called ethanol, which ends in OL, again, because it has 2 carbons. So this is what I was saying about earlier. Everything really does fall back to those first 10 alkanes, all the different functional groups that you come across, how they are named, and everything all come back to that. Any questions on that there? Here's a couple different isomers of pentane, which is 5 carbons. Come back. Which is basically each of these guys have 5 carbons and 12 hydrogens. So we'll go through the names again to show you how we get to the names. And we're not going to use the top names. Those are kind of like common names. So the guys in the parentheses are what are referred to as the IUPAC name. That's really sort of the formal way of naming things. That stands for the International Union of Pure and Applied Chemistry. Those are the guys that you can thank for helping to name everything and all the rules. Those are the 3 guys in a room that come up with all these rules. So let's see how we get to these names. So first one's pretty straightforward. We're just going to count our longest continuous carbon chain. So again, our longest carbon chain right there is going to be 5 in a row. There's absolutely nothing else attached there. And again, that would mean that it is pentane in this case. Our next one, we would look for the longest continuous carbon chain. Once again, we could go straight across is a good way to start. So that is 4. We also could, again, if we wanted to get the 4 by starting here and then going up, would also get us to 4. Once again, here you could choose either way. It doesn't really matter which way you choose, but once again, I'm going to go with the straightest one. Once we identify the longest continuous carbon chain, which in this case is 4, that is going to give us the base of the name here, which is butane. Now I want to look and see what type of groups I got hanging out there. And in this case, I have just this group right there hanging out. That is a 1 carbon group, as we just talked about, which is based off of methane. And because it's an alkyl group, it goes from methane to a methyl group. Once again, YL at the end of it, having 1 less hydrogen, allowing it to connect in. And that is where the methyl part comes into play. So that is where the methyl butane part of the name comes into play. Last thing we want to do is number the chain. And in this case, we got 2 options. We could go left to right, which would be 1, 2, 3, 4. We also can number right to left, which would be 1, 2, 3, and 4. Now, in the case of the red direction, that gives us a methyl group at carbon number 2. In the case of the blue direction, that gives us our methyl group at carbon number 3. And we always want to give the groups and alkanes the smallest number. That means that we would want to actually number in the red direction, and we would not want to go this way. And that would say that our group there would be at carbon number 2. And that gives us our 2, again, dash methyl, dash between number and letter, butane. Question on that one there. Looking at the last one, following the same steps, going straight across gives us 3. And in this case, you could get 3 multiple ways. You could go straight and then go up. You go straight, go down. You can actually just go up and down in the middle. There will get you 3. They're all going to be the same here. So 3 carbons is going to be our longest carbon chain. And that is going to give us the base of our name, which is going to be propane, which goes back to that list of 10. When we look now, we actually got a couple of things that are not part of the main chain, and it is those 2 guys right about there. And each of those guys separately are 1 carbon groups, which means they are each a methyl group. Now, since we actually have 2 methyl groups in the same compound, we do apply a prefix, and the prefix for 2 is di. So this would be dimethyl. And by the way, they do not have to be on the same carbon. The dimethyl just means that they are in the same compound. So they could be on different carbons if you want. And that again is where the dimethyl part of the name comes from. Yes. Yeah, it would change the number of the location where it's at. Yep. It would still be called dimethyl, even if there's just, if they're on different carbons. So we do have to give the location. In this case, you could go left to right, 1, 2, and 3. You could go right to left, 1, 2, and 3. And once again, in this particular case, it does not make a difference which way you go. Both of those are going to get you 2. And we do, as sort of the question was asked there, we do need to actually give the number twice, 1 for each carbon, even though they're hanging out on the same carbon. And that's why it is 2 again, comma 2, comma between 2 numbers, dash number to letter, dimethyl propane. Any questions on how we got to any of those names there? Now, all these guys have 5 carbons. All these guys have 12 hydrogens. They are all isomers of each other. They are all different compounds because they have different names, and that is a good way to do it. This is a situation where somebody may be tempted again to draw something like maybe this. Ran out of screen, but again, there's one to the left there that's off the screen, hydrogen. And another one on top that also went off the screen. Is this something different than something else I drew here? If we were to do our longest continuous carbon chain here, it would be 1 to 2 to 3 to 4 and to 5. So even though it looks all different drawn, it is still pentane. So these two are exactly the same to each other. The only difference is you just drew it differently to make it look different, but it's really not. So this is what I was saying earlier. A really good way if you're asked to draw some type of isomer is to draw them and then go and name them both. And again, if you do it correctly in the naming part and you end up with 2 different names, you did draw an isomer of each other. But if you did draw something like the guy on the left there and go, oh, I ended up with just pentane again, that is, again, not going to be an isomer of each other. Any questions on that there? Yes. There is no methyl on any of that guy on the left because the longest continuous carbon chain is the whole entire thing. Yep. Yep. So when you go for the longest continuous carbon chain, again, like the one there on the left, it doesn't have to be the straightest. The only thing you can't do is back up. So we start at the top and go all the way to the bottom. You hit 5, and that takes care of everybody there in terms of carbon. So there's no other carbons basically not part of that main chain. Other question? Yeah. Yeah, it could zigzag, it could, again, the only thing you can't really do, like I mentioned, is kind of backtrack. So, say you could start up here, come this way, come up this way, come this way, come this way, come this way, come that way, however many carbons that would be. And that would all be the one longest continuous carbon chain. The only thing you can't do is, for example, if you go this way and then you have something come this way and decide, well, I want to come back this way, back down to this way, you can't backtrack over it and stuff like that. So you got to go basically in one direction until you basically hit a wall. You can't go any further. And then that would be the total number of carbons that are in that run. Yeah. On this, the one on the far right. We know that because the longest continuous carbon chain is this. See, I'll put a box around it. Is this guy. So anything that is not part of that longest continuous carbon chain is considered a group that's attached. And that's how we know that this guy is a methyl group and this guy is a methyl group. We can't include those in the longest carbon chain because the only way to include it, I'll go with red here. The only way to include those guys, for example, is if we started here, 1, 2, 3, then we're backtracking now, right? Back down to 4, and we're backtracking again to 5, and we can't do that. So you can't backtrack over where you've been. So that's why they would not be included in that case. Yeah, so are you talking about anyone drawn here, or if you had like, yeah. If it was an L shape, you would need another. This guy would have to move over here, and then you'd probably have just one carbon group to make the L. So, if you had to come up to here, this guy would have to be over there to do that. And that would mean that you would just have this guy left. That would be the only group there. So, if you include another sort of carbon as part of the main group and you could do it sort of legally do it, and that no longer becomes a group. So it's part of that main chain. So anything part of the main chain is not considered a group. Anything that is not part of the main chain, the longest continuous carbon chain, is a group that's attached. Yes, sir. Yeah, so that's the rule. Is pretty much you just can't backtrack. Yeah. So it's very simple. You usually have like option of going left to right, then stopping, going right to left and stopping, going left and going up, or going left and going down. So you just, again, got to start in one direction, keep counting until you pretty much hit a wall. You can't go any further. Other questions? All right. These we hit already: hexane, heptane, octane, no name. So let's get into some more of this naming here to understand how we properly do these things. As I mentioned before, usually in most cases in organic chemistry, you're asked to give the IUPAC name, and that is sort of like the formal way of naming everything. One thing about organic compounds is there are like multiple names for the same thing. For example, if you had something like this guy here, if we took the IUPAC way of naming it, this is known as 2-propanol, which is an alcohol. It is also known sort of commonly as isopropyl alcohol. And it's even more commonly also known as rubbing alcohol, right? So those are all three basically same name for the same thing. So in organic chemistry, there's a lot of like historical names, there's a lot of common names. But a lot of the time you are usually asked to give the more sort of formal IUPAC way of naming things. Just an example of this as well. This right here is acetic acid. This is also what is known as ethanoic acid, which is the IUPAC way of naming, common name. And we commonly refer to a lot of times as basically vinegar. It's basically the major component in vinegar and stuff like that. So that's a carboxylic acid as well. So there's a lot of different naming. We're going to talk about the rules for IUPAC naming, which is pretty much the rules we just went over. You want your longest carbon chain. You want to find the groups that are there. And you want to number the chain to give the groups the smallest number. So always the longest carbon, as we talked about, is where you want to start with. And again, when you do that, it will match one of those 10 alkanes. And that's going to be really the base of your name there. Once you do that, again, you want to basically find the groups that are attached, those alkyl groups. And again, you could have a methyl group like we saw. It could have an ethyl group, which is a 2-carbon group, a propyl group, a pentyl group, and so forth. You want to number the chain to give the group the smallest number. So you may have multiple things attached there. So you want to number whichever way, left to right or right to left, up, down, up. That gives basically those groups the smallest number. Once you have that, we're going to put our groups in alphabetical order first, regardless of the number or the prefix. So again, it's possible to have, like, say, an ethyl group, which is E, and a methyl group, which is in the same compound. And maybe your ethyl is at carbon 5, and maybe your methyl is at carbon 2. You would do your ethyl first, even though that has a higher number. Again, maybe you have a ethyl group and 2 methyl groups in that compound. So that'd be ethyl and dimethyl. You would ignore the prefix di and go with ethyl first over the methyl part of it. So we ignore both of those things. Now, when you have an option of numbering one way or the other, And it doesn't really matter because both groups end up at the same numbers. You would want a number whichever way would be more alphabetical first. So you would want to give the alphabetical guy that comes first the smaller number in that case, if it happens to be that way. As I mentioned before, alkyl groups are groups that are basically carbon-based. They are those alkanes, again, that are missing a hydrogen that allows it to connect into the main chain without having too many bonds happening there. We get rid of the A and E on the alkane name and we put the YL. So once again, if we had a 2-carbon group, that is based off of ethane, and that would be a ethyl group that's attached. If you had a 3-carbon group, that would be a propyl group based off of propane, again, missing one hydrogen to allow it to connect in. So you could run through all those alkanes we just talked about, basically drop off a hydrogen, they become a group, and put a YL at the end of it, and that would be the proper name for each of those things, as we see here. Now, sometimes there are some special sort of group names, and it really depends on where the attachment occurs. And when we talk about carbons, we can actually identify carbons as what is known as primary, secondary, or tertiary carbons. So primary 1, secondary 2, and tertiary 3. And we can classify carbons that way. And the way that you classify the carbons or identify it as a primary, secondary, or tertiary carbon is fairly straightforward. Let's say we're looking at this carbon. This carbon is directly attached to one other carbon. That would be a primary carbon. If we look at this carbon and we find it attached directly to 2 other carbons, that is a secondary carbon. And if we're looking at this carbon and it is directly attached to 3 carbons, that is what is referred to as a tertiary carbon. Personally, me, I go with the counting of the carbons. Some people count hydrogens to do this, so it's the same thing. If you were doing hydrogens, you would have 3 hydrogens for a primary, 2 for a secondary, and 1 for a tertiary, but I think counting carbons is a little bit more straightforward. So for example, if we look over here at this carbon would be a primary carbon. It is directly attached to one other carbon in this particular case. So how does this affect certain groups? It affects certain groups based on sort of the connectivity. So if we looked at our propane there, and let's say we had what is sometimes referred to as a normal propyl group, which looks something like this. The connection is going to occur right here on this carbon. And this carbon here would be a primary carbon, right? As is attached directly to that carbon right there. And that would be a primary carbon. If we take the same propyl group, but instead of attaching to the end carbons, either end, but we have the connection actually occurring right there on the center carbon. That carbon right there in the center, is it a primary, secondary, or tertiary carbon? It is a secondary carbon. This guy right here is directly attached to this carbon, and he's directly attached to that carbon. This guy would be a secondary carbon. So that attachment through the secondary carbon actually gives us a different historical group, which is known as isopropyl. So this is known as isopropyl. This is a very common sort of group that comes across a lot, and people actually still use isopropyl more than the actual name of it. And it's a lot of times in sort of condensed form that looks like this: CH3, CH, CH3. So that is like the isopropyl group, and that's a very common one. So in the case of like a normal propyl group, we're attaching at the primary carbon at the end. In the case of the isopropyl group there, we're attaching to the secondary carbon, and again, it gives them a little bit different. So here's sort of our normal methyl, ethyl, propyl, butyl type groups. Again, these are all going to be attached to the primary carbon at the end. And here's a table that shows some of those special ones that we just talked about. Here's our isopropyl, which is attached to the secondary guy. This is sec-butyl. That's basically a butyl group that's attached, sec meaning secondary. So that is the secondary carbon where the attachment occurs. And that's this guy right here, attached to one carbon and two carbons. T-butyl is tert-butyl, which is tertiary, which means it is attached to the tertiary carbon, which is this guy right here that's attached to there, and there. So sometimes you come across these guys, and these guys are really the sort of historical names that people use still, the common names. These are actually the IUPAC way of naming these groups, but pretty much nobody ever uses these. Most people will roll with these. So if you see these kind of weird names or stranger type names, these are sort of really common names or historical type names that are used still a lot. And even the IUPAC recognizes really this guy because it's used so much. Any questions on groups there? All right, so let's take a look at this guy here. We're going to look for our longest continuous carbon chain. And this is going to be 1, 2, 3, 4, 5, 6. We could also get 6 by starting to the right and then going up. So either way, you could get 6. Once again, that is going to be your longest continuous carbon chain, and that is going to be the base of the name, which once again will be hexane, which is 6 carbons. We are now going to be looking for what is attached there that is not directly part of that main chain. And in this case, it is only this one carbon group here, which is going to be our methyl group based off of methane. So this would be our methyl group. And we would add that to our name here, methyl hexane. We do now need to number this, and you could probably just visually see that if you go left to right here, that's going to be 1, 2, 3, 4, 5, 6, as opposed to if you went right to left, 1, 2, 3, 4, 5, 6. So going left to right, our group has a 2, which is a smaller number than left, right to left, which is 5. And it is as simple as that, that 2 is smaller than 5. And we would put that 2 in there with the dash, and this would be 2-methyl hexane in this case. Now, not all groups do have to be or will be carbon-based. Halogens are oftentimes involved in organic chemistry. So our halogens, which is our group 7, F is fluoryl, Cl is chloral, Br is bromol, I is iodo. So these guys get involved as well. So if you have any of these sort of halogens, it's fluoryl, chloral, bromol, iodo is how you would name those. You would do the same way, alphabetical order with everybody else that might be there. Again, whichever way gives those groups the smaller number. And again, if you had multiple to those, you would also use a prefix like di or tri or maybe. I get 2 for methyl because the yellow is the main chain, and the guy that's in green there is the group that's attached. So we have really 2 ways of numbering. We can number left to right. If we do that from left to right, that methyl group ends up at carbon number 2. If we number right to left that chain, the methyl group ends up at carbon number 5. The purpose of numbering is to give the groups and alkanes the smaller number. So going not in this direction, but in actually this direction, will give that methyl group the smaller number of 2, and that's what we would want. And really the 2, like I said, really naming is all about location, location, location. So you're basically telling people, hexane, I got like 6 carbons in a row, and on the second carbon, there's a methyl group hanging out. That's basically what the name basically says. Other questions on that? Okay. All right. Why don't let me try some here. I think we talked about. And again, these are some of the stuff we talked about. Multiples of the same group doesn't have to be on the same carbon, but di for 2, tri for 3, tetra for 4, kind of similar to the prefixes we used with non-metal naming. All right. All right, that's the one we just did. All right, so why don't you give this one a go, see what you come up with here. So I believe 6 will be a winner on this one. 1, 2, 3, 4, 5, 6. Again, you can also get 6 going this way. 1, 2, 3, 4, 5, 6. So again, there's a couple different ways you can kind of get to 6, but I think 6 is the longest no matter which way you go. And once again, you could choose it either way. It doesn't really matter. It should come out the same. So once again, the base of our name here is going to be 6 carbons, which means we are going to have hexane happening. We have a group right there and a group right there. They are each now 1 carbon groups, which is based off of methane, and that would be a methyl group. That would also be a methyl group. And once again, we have multiple of the same group in this guy, which is 2 of them. So that will turn that into a dimethyl situation. Any questions so far? What we want to do is number. So we'll start just left to right here. So that's going to be 1, 2, 3, 4, 5, and 6. So going in sort of the red direction, we end up with groups at 2 and 3. Our other option would be obviously to roll the other way in terms of numbering, which would be 1, 2, 3, 4, 5, and 6. Going in sort of the green direction, we end up with groups of 4 and 5 would put those 2 groups. The way we would want to go is which way? We would want to go the red way. It is as simple as 2 is less than 4, basically. Yeah. So we would want to go in the red direction and number this way. That means that we would have a methyl at carbon number 2, comma, carbon number 3. We need to give location of both of them. We'll do a dash between the number and the letter, which would be dimethyl. And then we will finish it out with hexane. So that would be 2, 3 dimethyl hexane. Any questions on there? Okay, why don't you try a few more here? I think we got. They agree with us, so that's good. Actually, we'll do these. There's 3 different ones here. Give it a go, see what you come up with. Give the IUPAC name for each of these guys. 1 there, and 1 there. Okay, let's take a look. We'll start top 1 there. I think there's lots of different ways you get there, but I think 6 is a winner there. 1, 2, 3, 4, 5, and 6 going straight across. Again, I think you can get 6 a number of different ways. And once again, you can choose either way you like. That is our main chain. That means we got a 1 carbon group here that's attached. We also got a 2 carbon group that's attached right there. We'll start with the main part of the name, which is the longest chain. That is 6, 1, 2, 3, 4, 5, 6. So the base of it is going to be hexane. We have once again a 1 carbon group, which would be a methyl group. We have a 2 carbon group that is based off of ethane, which would then be a ethyl group. We do want to number this. So if we number left to right, that would be carbon 1, that would be carbon 2, that would be carbon 3, 4, 5, and 6. So if we went left to right, we got a group at 3 and 5. If we number the other way, we go 1, 2, 3, 4, 5, and 6. Going right to left puts our groups at carbon number 2 and carbon number 4. We should go which way? Yeah, we should go right to left, 2 and 4. Again, it is as simple as 2 is smaller than 3 in that case. So that is the way that we would want to number here, not the top way. So that means our methyl here would end up being carbon number 2. Our ethyl would be carbon number 4. And now we got really all the parts here. We just need to put it in alphabetical order, regardless of the number. So ethyl is going to come first here. So this guy here would be a 4-ethyl dash 2-methyl and hexane. Yeah. Any questions on that there? Yes. It does. So it should go alphabetical. So it goes alphabetical regardless of number or prefix. So if they happen to have like a di or a tri, you would ignore that and just go with the name of the group. Yeah. So it's definitely alphabetical. Other questions? All right. So let's take a look at the guy on the left there. And I think on this one, it is going to be just starting at the bottom here. 1, 2, 3, hanging a right, 4, 5, 6, 7. I think actually is the longest there. So 7 is our longest carbon chain. That leaves just this guy here that is not part of it, which again is a 1 carbon group. We'll start with the base of the name, which is based off of that longest carbon chain, which is 7. So that is going to be a heptane situation. We once again have our methyl group that is here. So that's going to be like a methyl heptane. Now we just want to nail down the number here. So going kind of bottom up, we go 1, 2, 3, 4, 5. Right, 1, 2, 3, 4, 5. There you go. 6, 7. Going the other way, 1, 2, 3, 4, 5, 6, and 7. We would want to go in this direction as it will give our methyl group the smaller number, which is 3. And this would be 3-methyl heptane. Any questions on that name there? All right, last one here. There, just go straight across. We got 1, 2, 3, 4, 5, 6. Not bad. If we go straight across here, 1, 2, 3, 4, and go up 5, 6, 7. Not bad. If we go 1, 2, 3, 4, 5, 6, 7, 8, even better. So there's actually 8 of them there. Again, you do want to check all your different options, as it again may not always be the straightest. So I'm going to go with that guy. It looks like a winner, and we get rid of all the other scribble there. So our longest carbon chain actually starts up here, comes down, goes over, comes back up, and goes over one more time. So once again, I did not backtrack there. And we do have our 8 carbons that are there, giving us. So if your question is, can you go this way, this way, this way, and then come back down?
No, not that.
Or go this way?
No. So in the second one from the go down.
Let's see here. Yeah. Oh, I see what you're saying. So you want to know? Can you go 1, 2, 3, 4, 5, 6, 7 like that?
No. So it's down 3 and then right 2 like before. Up,
Yeah.
right, down, right. I think it's
You can't. So so if you're coming this way, this way, this way, and then you want to go,
right one, then down.
you can't, because there's no connection here. So they're not connected, so you can't go down. Yeah. So the only place you go once you go that way is to the end, which would get you 8. Yeah. If there happened to be a line or something there, then you could go down, but because they're not really connected, there's no bond there, you cannot go down. Other questions on that? All right, so that is going to be our 8 there, which will give us octane as our base. We have a methyl group here. We have a ethyl group there. And now we need to do some numbering of these guys. So we're going to start up on top. We'll go 1, 2, 3, 4, 5, 6, 7, 8. Going that way gives us groups at 3 and 5. If we start on the right, 1, 2, 3, 4, 5, 6, 7, and 8. That gives us groups at 4, I think, and 6. So clearly that is larger. So we do want to go in this direction, which would be coming this way. That is going to give our methyl a 3, and that's going to give our ethyl a 5. Once again, we're gonna go alphabetical first, so we're gonna go with the ethyl. So that would be 5-ethyl, 3-methyl octane. Any questions on that one there? All right. Any questions on naming there? Let's get this. Let's talk a little bit about drawing if you have the name. So when you want to draw, if you have the name, it's actually, I think, easier of everything else. So let me show you how we would approach the first one here. Whenever you have the name and you want to draw it, so in this case, we're going to draw the condensed formula, which is basically not drawing out the hydrogens. You always want to start backwards. So the back part of the name is butane, and butane tells us it is 4 carbons. So that is where you want to start, really just the 4 carbons. And that really takes care of the butane part. Since you were drawing it, you could call the guy on the left carbon number 1. You could call the guy on the right carbon number 1. It doesn't matter. So for me, I'm going to call the guy on the left carbon number 1. And what it means 2, 3 is I go to carbon number 2 and I should find a methyl group there. Takes care of the 2. I also go to carbon number 3, which in my case would be right here. I should also find a methyl group there. That takes care of pretty much the entire name. Everything else at this point is going to be hydrogens to get carbon to 4 bonds. So if we look at the carbon on the far right, it has 1 line coming in, which means it will need 3 hydrogens to get the 4. Carbon next to it has 3 lines coming in, which means it needs 1 hydrogen. Carbon next to it has 3 lines coming in, needs 1 hydrogen. Carbon next to that, 1 line coming in, needs 3 hydrogens there to fill it out. So always work backwards in the name and then fill in everything else at the end with hydrogens to get carbon to 4. Question on that one there. All right, why don't you try the other 2 there and see what you come up with. Get in. Let's take a look. Once again, you can start backwards. We're going to go with heptane. So heptane tells us it's 7 carbons. Let's start over here. 2, 3, 4, 5, 6, and 7. Takes care of that. I'm again going to call the guy on the left 1, but you could do the other guy as 1. 2-methyl means I go to carbon number 2 and I should put a methyl group there. So that takes care of that. Carbon number 3, which would be right next door, would have an ethyl group, which is a 2 carbon group, which looks something like that. At this point, we're done pretty much with the name. Everybody else is going to be hydrogen to get the 4. Guy on the far right will need 3 hydrogens. Guy has 2 lines coming in next to it, means it needs 2 to get the 4. 2 lines coming in, needs 2 hydrogens to get the 4. 2 lines coming in, needs 2 to get the 4. Guy next to it has 3 lines coming in, needs just 1 hydrogen to get the 4 bonds. Same thing with the guy next to it, and the guy at the very end there needs 3 as it has 1 coming in. Any questions on that? Yes. Yeah, it is. I think they threw an extra dash in there for free. I think, yeah. So it should just be ethyl. You don't actually need the dash between those 2 days. Other questions? All right, looking at the last one here, which is pentane, heading in this direction. We're going to 5-carbonate because that is pentane. Once again, that takes care of that. Once again, I'm going to go number 1 right there, which means my number 2 would have a chloral, which is a chlorine. And my number 4, which would be back over here, would have a methyl group, which is our 1 carbon group. And now we're ready just to fill in our hydrogens. Guy needs 3 at the end, needs 1, needs 2, needs 1, and needs 3. So really sort of the drawing part is pretty straightforward. It kind of tells you what to draw, which is pretty good. Any questions on naming or drawing? We also talked about cycloalkanes the other day as well. So these are just ring structures. So, you know, for example, if you had something like methyl cyclopropane, you would do the same thing. Starting this way, cyclopropane. Propane means 3 carbons. Cyclo means in a ring. So you could draw almost like a triangle here. And methyl means you could pretty much put it at any carbon you like. You could put it at the top one. And we would still fill in our hydrogens like normal. This guy would need 2. This guy would need 1. And this guy would need just 1 up the top. I'm sorry, 2 on the bottom. Remember the cycloalkanes are usually just drawn more in line structure, like the triangle, and you would do just like something like that. Would be like that. Any questions on naming or drawing? All right, well, I think that's good. That wraps up Chem 2A for the season, I think. Yes.